Similar to RF DAC, digital and mixed signal techniques have also been used to design power amplifiers. These are called as digital power amplifier or digital PA. The idea is that we can use highly efficient power amplifiers, which also turn out to be nonlinear. And we will find that the transistors in these power amplifiers start acting like switches. So by using such kind of nonlinear switching power amplifiers, if we can still achieve amplitude modulation using only digital looking signals where the input will be going between rail to rail, then we can design power amplifiers which are not only efficient but also they can enable amplitude modulation. So if you remember from the discussion about the classes of power amplifier, we had one transistor and then there was some biasing and matching network through which load was connected. Now here if we observe this current IDS and voltage VDS of this MOSFET, then we can find out what is the power dissipation in this input element. So we are applying a signal here, resulting in IDS and some VDS. So by looking at the power dissipation in this M1, we can talk about the overall efficiency of this entire power amplifier, because the power which comes from the supply goes to the load and to this transistor. The biasing and the matching network is supposed to be lossless. So if we can ensure that the power which is dissipated across this transistor is minimized, then we will be sure that the entire input power from the supply goes to the load and we can achieve efficiency which is close to 100%. So if we take a generic case where there is some VDS and IDS, let's see, it looks like this. See the VDS and the IDS, let's say, looks like this. Then we can find the power dissipation in this M1 as the product of this VDS and IDS. So by looking at this waveform, we can see that when the current is going high, it means the transistor is in a highly conducting state. Then the VDS also drops. Whereas when the transistor becomes less conductive, then the current reduces while the voltage across the transistor increases. So this is a very generic scenario. So if you look at the product of VDS and IDS, which is, let's call it as P loss, then that product is going to have some peaks whenever the IDS as well as VDS are non-zero. So it may look like this. And the total energy lost per cycle we can find out by integrating this area under the curve. So looking at this waveform of VDS and IDS, we can easily figure out that if we can ensure only one of them is non-zero at all the times, then the product will always be zero. And in such a scenario, we can minimize the loss which is happening in the transistor. Power dissipated in M1. By engineering or shaping VDS and IDS such that both VDS and IDS are non-zero at the same time. So this will result in minimizing P loss across the transistor to result in high efficiency. So by controlling the shape of this VDS and IDS, we obtain different category of power amplifiers. And these are also called as switching power amplifier because we'll find that if we completely turn on this MOSFET, then we are going to get VDS which is close to zero. And when we completely turn off this M1 in the other half, then this IDS is also going to approach zero. This is achieved by operating the transistor as a switch. And this operating the transistor as a switch is not always sufficient because still there will be some transition region in which the voltage and currents are going to be non-zero at the same time. So in addition to that, this output network at the drain can be engineered such that only when the VDS has become completely zero for this IDS to peak, and only when the current has become fully zero, then only this VDS to peak. So we operate the MOSFET as a switch, and at the same time design load network force non-overlapping VDS IDS. Okay, so here we can observe that if this MOSFET is acting as a switch, here we are pushing it into deep triode or cutoff, then the input signal will not have much information in the amplitude. So the amplitude will only just tell when the transistor needs to be turned on or off. So such kind of switching power amplifiers cannot support amplitude modulated signal, can only support phase modulated signals which are also have a constant envelope. Switching PAs, there are also classes within the switching PAs. Their classes are called class D, E, F. Then there are some variants of this classes as well. Switching PA cannot support AM signal only phase info of input signal is used to generate output. Same time, efficiency approaches 100% under ideal condition. So because of this reason, there is a lot of motivation of using switching PAs as the efficiency is very high. And by using the digital and mixed signal technique, we will try to see how the switching PAs can be modified to support amplitude modulated or non-constant envelope signals as well. PPA uses non-linear to enable amplitude modulation, bring in high efficiency. So earlier we have seen that when we categorize the power amplifiers based on the conduction angle, then there was a strong trade-off between the linearity and efficiency, and we saw that we can get an efficiency as high as 50% under ideal scenario while using class A, which can enable amplitude modulation. But if we want to improve the efficiency further, we had to trade off the linearity. Using the digital PA, we are getting an alternative where we are using highly nonlinear switching PAs, which are designed for high efficiency. But at the same time, we are trying to use some digital technique to see if amplitude modulation can still be supported. Let us look at the complex modulated signal, which needs to be amplified by a power amplifier. The complex modulated signal will have amplitude modulation as well as phase modulation. AM, and this is the PM. Now we know that a switching power amplifier will completely ignore this AM part. Okay, and if such a signal is fed to a switching PA, then output will only be containing the phase modulated information. The envelope or the AM information is going to be completely lost. So what we can do is, you can take this input signal, which is complex modulated, and split the AM and PM information separately. So we can get the separate envelope information, which is in this A of t, and another signal which is having a constant envelope but containing the phase information. So now we can feed this PM signal to the switching PA directly. This is the switching PA. See, which is driving the antenna. But this AM information needs to be also given to the PA so as to allow the envelope to change. So we need another control to this switching PA where the envelope can change. So this is let's say envelope control. So if this envelope control is present in this kind of switching power amplifiers, then it is possible that we can finally get a non-constant envelope modulated signal while using switching power amplifiers. So we will be having high efficiency as well as an amplitude modulation. Now this envelope control can be enabled using a digital technique. So what we can do is, we can have multiple units of the switching PA. Finally, we can add the power. Like that. All the switching PAs can easily accept the phase modulated signal. While we can have a digital control to enable or disable these unit cells so as to control the net power at the output. Digital control to enable, disable unit cell. So these are switching PA unit cells. Now we can see that this phase information is directly fed to the input of the switching power amplifiers, but by splitting the PAs into these unit cells and having a digital control, now we can also achieve and control over the envelope, or we can get amplitude modulation. Amplitude modulation. Okay, we have got PM as well as AM. So this is the overall architecture of most of the digital PAs which are present in the literature, and there are different ways where these unit cells are designed and the digital controls are added to the PS.